Often in mathematics and science, we use equations that involve more than one variable to describe a relationship between multiple quantities that might change over time or just take on different quantities and have a relationship with one another. These are often called formulas because they aren't something that you solve for a particular variable in general. They're describing a relationship between them. So, for example, there's a fact called the ideal gas law in physics that describes how various quantities related to a gas inside an enclosed container, like a balloon, are related to one another. So the ideal gas law can be written in symbols as PV equals KT, where each one of these symbols has a particular meaning. P is the pressure exerted by this gas on the exterior of whatever container is holding it. V is the volume of that container, and so it could get bigger, it could get smaller. K is just a constant, which depends on the specific gas that you're using. Different types of gas will have a different value of K here, but as long as the gas is the same, that K will be a constant. And T is the temperature of the gas. So this is saying that as long as we fix a gas, there's a particular value K, this constant K, such that the pressure times the volume is always equal to that constant times the temperature. And so there are some things that we can see about this. We can see that, okay, let's say if the pressure stays the same and the volume goes up, well, then that means that the left-hand side of the equation is going to be going up, which means that the right-hand side of the equation is going to go up as well because they have to be equal to each other. But since K doesn't change, K is a constant, that means that the temperature has to go up. So this tells you that if you've got a gas and the pressure stays the same and the volume goes up, then the temperature also has to go up. And there are, of course, lots of other ways that you can work this out. And what we may have is a situation where we ask the following question. Given a particular volume and temperature, what is the pressure of the gas? So, for example, let's say, and I'm not going to work with any units here. Let's suppose that the volume was 10, the temperature was 20, and let's say K equals 5 for some made-up gas that we're looking at. Well, if that's the case, then this would mean that we could replace three of the values in our ideal gas law with our values for V, T, and K to get that P times 10 equals 5 times 20. Or if we simplify this a bit, we can write this as 10P equals 100. And so, if we have that, then we can figure out what the pressure is. We can divide both sides by 10 to find out that in this case, the pressure would have to be 10 of whatever units we happen to be using here. And we could ask the same thing, but what if the volume is 10, the temperature is 25? What if the volume is 50, but the temperature is only 2? Things like this, we could ask again and again what the pressure is going to be for a given volume and temperature. Rather than going through this process of solving for P every single time, what we can do instead to make things easier on ourselves is we can solve for the pressure. we can solve for one of the variables in the equation. So we can solve for P instead of going through this process every single time we come up with a new volume and temperature. And what that means is getting P by itself. Coming up with an equivalent equation using all of our rules of algebra, adding, subtracting, multiplying, and dividing from both sides of an equation, but where we want to get P by itself. So let's go ahead and do that. So let's try to solve the equation PV equals KT for P. Now this isn't going to be too difficult. This is a fairly simple equation, fairly simple formula, but we'll do some slightly more complex ones in a second. We want to get P by itself. And so once again, we want to think in the following way. What's currently happening to the P on its side of the equation, and how can we undo all those things? Now, in this case, you'll notice there are no numbers involved, but that's okay. We're just trying to get this letter P by itself, this variable P by itself. And the other side of the equation is going to involve a bunch of variables, but that's all right. That's what we're trying for, actually. So right now we ask, what's happening to P? P is being multiplied by V. Well, what's the opposite of multiplying by V? Well, we don't know what V is. But whatever V is, the opposite of multiplying by V is going to be dividing by V. So what we can do is divide both sides of this equation by V. Once again, we're allowed to do that. We're allowed to multiply or divide both sides of an equation by any number we want other than 0. But a volume of 0 doesn't make sense in the context of the problem, so we're okay. So if we divide both sides by V, then on the left-hand side, we've canceled out everything in the problem except for P, which means we're left with just P equals KT over V. And we're done. We have successfully solved this equation for P. And now the reason why we might want to do this is, as we said before, we might have a big collection of temperatures and volumes that we want to calculate the pressures for over and over again. Well, now we can do that by plugging all those temperatures and volumes into the formula KT over V, which always gives you the pressure. So this is the basic idea behind solving a formula for a variable. You want to get that variable by itself. And that's pretty much it. We're just going to use the same techniques of solving equations that we've been working with. Let's do a couple more examples. You may be familiar with the conversion between Fahrenheit and Celsius, the two ways we have of measuring temperature. And so you may be familiar with the formula that the degrees Fahrenheit is equal to 9/5 times the degrees Celsius plus 32. So here F equals degrees Fahrenheit, and C equals the degrees Celsius. And currently this formula is solved for F. If I asked you to solve this formula for F, then you'd just give me right back exactly that equation and you'd be done. We can do a little bit better, of course, and I can ask you for something else, and I can ask you to solve for C. So to solve for C, we're going to try to get C by itself. And there are a couple of ways of doing this. Now I want to take this opportunity to illustrate one technique that winds up being very helpful whenever we're dealing with fractions like we are here. So we've got f equals 9/5 c plus 32, and we want to get c by itself. Now, one thing that we could do at this point is to clear denominators, multiply everything by 5, because that's the denominator of the fraction involved. We could do that, and that wouldn't be a bad thing to do at all. I'm going to do things slightly differently, though, for the sake of illustrating a technique. We want to get c by itself, so we're going to start off by subtracting 32 from both sides. We're trying to get the c by itself. This plus 32 is sitting over here. Let's just move it to the other side and be done with it. So we have f minus 32 equals 9/5 c. So now the question is, how do we get the c by itself? Now, we ask, what is c currently doing? What's currently happening to the c? And we see currently c is being multiplied by 9/5. So what's the opposite of multiplying by 9/5? Well, dividing by 9/5, of course. However, dividing by a fraction always carries with it a certain amount of complexity. You get fractions and denominators, you've got to flip and multiply, things like this. So I want to get us in the habit of doing the following. The opposite of multiplying by 9/5 is actually multiplying by 5/9. Multiplying by a fraction is the opposite of multiplying by that fraction's reciprocal. So if I'm multiplying by 5/9 currently, I can undo that by multiplying by the reciprocal of that fraction. So what I want to do in this case is I actually want to multiply both sides of this equation by 5/9 and go from there. This is going to turn out to be a lot less work than dividing by 9/5. So when we're working with fractions, usually instead of dividing by fractions, we want to multiply by their reciprocal because it means the same thing. It does the same thing. And let's see why. Let's see what happens here. When we multiply 5/9 by 9/5, the 5's will cancel and the 9's will cancel. Which means that on the right-hand side of this equation, we get just c, which means we've done our job. We have solved for c. Now the right-hand side looks like 5/9 times f minus 32. And unless you're given instructions to the contrary, this is a perfectly fine way of leaving your answer. Unless you're given instructions to the contrary, go ahead and leave your answer like this. We often work with formulas that have parentheses in them that aren't all distributed out. You could distribute things out if you like, but it actually makes it less useful to work with. Makes it look less good. So this is a perfectly good answer. But you could also, if you wanted, distribute the 5/9 through and get this left-hand side is 5/9 f minus, and then you wind up getting 160 over 9 equals c. This is also an acceptable answer, but I claim that it's not quite as pretty as the first one that we got, the one in the blue box. And mathematicians like pretty formulas. So usually the pretty formulas are easier to work with, and so usually we'd actually leave it in the form on the second to last line on the page. All right, last example, and one that doesn't have any particular application or interpretation to it. Let's solve zt over z plus x equals c for z. Let me move that up here. So in this case, we want to get z by itself. That's our whole goal. The t's, the x's, the c's, they're going to be running around. It's okay. We're going to hopefully gather them all on one side of the equation and leave the z's by themselves. Now, once again, there aren't any numbers involved, and so this is going to look a little abstract. The thing to remember is that the variables are always standing for real numbers, which means they follow all the same rules that real numbers do. All the rules that real numbers do, these ones follow also. So we can go through the similar sort of process here as we do whenever we're solving any equation. So for instance, when I look at zt over z plus x equals c, the first thing that I want to do is get those z's out of the denominator. We can't solve for a variable that's in a denominator. So to get the z out of the denominator, I'm going to multiply both sides. So I'm going to multiply the left-hand side by z plus x, and I'm going to multiply the right-hand side by z plus x. Why can I do that? Because I can multiply both sides by anything that I want to. And in this case, it happens to be convenient for me to multiply both sides by z plus x so that I can cancel them. So that means that on the left-hand side of my equation, I'll just get zt, and on the right-hand side, I'll get c times z plus x. Now in this case, I will want to distribute this through because I haven't gotten all my z's on one side yet, so I'm going to have to work on that. So zt is equal to cz plus cx. Again, we want to get the z's on one side. So what we can do is we can subtract cz from both sides of the equation and get zt minus cz is equal to cx. Now this looks a little odd because we have no numbers involved and we're just moving the variables around, but you'll notice that at each step we're just using the facts that we already know about equations. That we can multiply or divide both sides by the same thing. We can add or divide both sides by the same thing. And what we need to remember is that that same thing that we're adding, subtracting, multiplying, or dividing doesn't have to be a number. It can be an expression. It can be an expression that doesn't have any numbers in it at all, like cz, zt, cx, these things. All right, so now we get to the step that is a little bit unique just to this form of the problem. We've got a step here that we don't usually need to worry about when we're solving an equation with only one variable in it. We run into it here where we've got multiple variables and we're trying to solve for one of them. So it's important here that once you have all of the target variable, by target variable I mean the thing that you are solving for. Once you have all of the target variable on one side, you want to factor it out of that side. So we're going to factor out using factoring of greatest common factors. So on the left-hand side of the equation here, we have a z in both of the terms. We have a zt and a cz. So we can factor a z out. This is the same as z times t minus c. And remember that factoring is just reverse distribution. If you're ever unsure whether you factored properly, you can check yourself by saying, if I distributed this z back in to the term, would I get the exact same left-hand side that I did before? And you do. You do. Z times t is zt, and z times negative c is negative cz or zc. The order of multiplication doesn't matter. So we get to this point where we have z times t minus c equals cx. And now we're almost there. We're trying to get z by itself. Right now we have that z times something equals cz. So we get z by itself by dividing by t minus c. We're allowed to divide by any expression we want, including expressions like t minus c. Now, it's only helpful to divide by expressions that are factors of whatever side you're working with, but that's the case here. T minus c is a factor of the numerator on the left, and so it will factor by the it will cancel rather with the factor of t minus c in the denominator. And so as a result, we get that z is equal to cx divided by t minus c. And that's our solution. We've solved for z. We have gotten z by itself on one side. And so if we want to know the value of z, given the values of c, x, and t, we can by plugging them into this formula here. And that's really where the benefit to solving for a variable comes from.